to establish what the octet rule is and what it means, and how ionic bonding goes into play with that. We are finally going to put all of this jargon about electrons and periodic table trends, we're going to start to put it into use and practice when we start to look at how different elements bond with each other. So today is going to be the intro into that. Okay, so why do chemical elements even choose to bond? What's the purpose? Well, the reason is that we've got these noble gas atoms, and these noble gases, remember, they're super inert. You put them in the sandbox, they don't want to play with anyone, okay? They're happy just the way they are. They don't want to participate in anything, and that the reason is because their s and p orbitals are completely filled. The s holds 2, the p holds 6. That's a total of 8 electrons. So we call that an octet because an octopus has 8 legs and an octagon has 8 sides. An octet is 8 electrons. All right, so there are these other elements and they're super envious of their noble gases and their amazing octet status. So what they have to do is they have to bind or combine themselves with other elements in order to fill their s and p orbitals. And they go about this through different ways. And we are going to talk about the different ways that they do that throughout this unit. So to try to fill these octets, chemical compounds form. Okay, now compound is different from an element. A compound is the amalgamation of more than one element. So it is the bonding or binding of more than one element together to form a compound. So compounds form so that atoms, individual atoms, can either gain electrons, they can lose electrons, or they can share electrons so that they have 8 electrons in their outer energy level. All these atoms are going to combine and shift their electrons around so that they can get closer to that octet and try to fulfill that octet. 8, okay. All right, 8 is great. All right, so let's remember these trends. All right, we had different ways to classify elements on the periodic table. And we obviously had different trends that we looked at. One way to classify the periodic table was between metals and nonmetals. Now, metals on the periodic table fall on the left-hand side of the periodic table. And the reason that we call them metals is because they're kind of loosely hanging on to their electrons, okay? Especially when you look at these alkali metals, the alkali earth metals, like they have 1 or 2 valence electrons. They really don't hang on to them very tight, right? So the energy to pull them off, remember ionization energy, is quite low over here because these would rather just get rid of a couple electrons in order to fulfill their 8 rather than to, I don't know, say gain 7 or 6 electrons. It's much easier for them to get rid of a few rather than gain a bunch. So we call them the losers, okay? Then over here we have, sorry, on the right-hand side of the periodic table, we've got the nonmetals over here. So here are our metals, here are our nonmetals. Over here in the nonmetal portion, they have, 6, 7 valence electrons in their outer shell. So it's much easier for them to just gain 1 or 2 rather than to get rid of 7 or 6. So we call these guys the gainers. Again, metals over here on the left-hand side. Let me see if I can write it. I'm new to this. Metals. Oh, nice. Super nice writing. Metals. Right? You guys remember this? And over here on the right-hand side, we have nonmetals. Oh my gosh, my writing is amazing. You can thank me later. This is going to be incredible. All right, so metals on the left, nonmetals on the right. Metals, they like to lose their electrons, right? They like to give them up. Nonmetals, they like to take. So remember electronegativity, that is how attractive these atoms are to electrons, like how bad do they want these electrons. Remember, Father Fluorine was the most electronegative, and it also had the highest ionization energy, which makes total sense because it does not want to get rid of its valence electrons. It just wants one more. Okay, enough of that. All right, so again, metals are the losers, non-metals the gainers. Okay, so but let's talk about a few exceptions to the rule because there's always exceptions to the rule. All right, hydrogen and helium. These are a couple exceptions because they only have that one S to fill. That means that they only need 2 electrons to fill their outer energy level. That's when they're the happiest. All right, then we have boron and beryllium. They tend to form bonds so that they have 6 electrons around it rather than 8. They do this really funky thing so that they're pretty happy with 6 electrons rather than 8. And then we have all of those elements with the d orbital. That d orbital always throws a wrench into the system. Now those elements with the d orbital, they can use that d orbital for bonding. And by doing that, it's going to allow for more than 8 electrons to bond. So now, when you get into the d orbital, everything gets just a little bit sloppy and more difficult to predict as to how they're going to bond because they can bond with more than 8 electrons. So let's talk about how we depict or how do we draw the notation, or how are we gonna picture all this, right? So we're going to use something that we call electron dot notation. For the very first thing we're going to start with are the valence electrons. Now remember, you all know that the valence electrons are the electrons in the outermost shell. If you don't know this by now, I feel bad for you. Okay, how do you know how many valence electrons an element has? Well, if it's in the S or the P block, the group number will tell us how many valence electrons it has. If it's not in the S or P block, of course, it's going to get kind of messy. So then we use this thing called electron dot notation. And this is a way to write an element by showing just the valence electrons on the outside. We don't need to know about those inner electrons. We just want to know about those that are going to be available for bonding, and those are going to be the valence electrons. Those are the ones that we are most curious about. Excuse me. All right, so how do I draw a Lewis dot diagram for a single atom? We've done this. This should be a review. If not, let's do it again. All right, for a single atom, the very first thing you're going to do is you're going to determine the number of valence electrons. And the way that we do that is we look at the group number. On an old school periodic table, the group number will tell us the number of electrons, except for those transition metals, because they just seem to be super fun. On the new school periodic table, groups 1 and 2 have 1 and 2 valence electrons. They're the same. But for groups 13 through 18, those that are over in that P block, the number of valence electrons is the second number of the group number. Another way to remember that is to take the group number minus 10. Okay, so if it's group number 18, our noble gases, 18 minus 10 equals 8, okay? Or if you look at the number 18, the second number is 8, so that means that it has 8 valence electrons. And we know that that's true because they are in the noble gases and their octet is fulfilled. Half of this recording may be me coughing. You're welcome. Here's an example. Group 14 has 4 valence electrons. So again, second number of the group, or 14 minus 10. All right, and then we put in the order of the dots. Okay, so for an example, oxygen is in group 16. Oxygen has 6 valence electrons. Okay, so the way that we're going to depict them is we are going to, I'm going to use red because it's easier to see. I like to go in a counterclockwise fashion, as it says, and you're going to go on the 4 cardinal directions, north, east, south, west, as you place the dots. So you're going to start, 1, 2, 3, 4, 5, 6 if we were doing oxygen. Okay, that's how we would depict it. It doesn't really matter, just as long as you place them in the 4 cardinal directions. Once we get into bonding, and you place them only with pairs. Okay, we don't place 3 or more together. We place them in pairs on the north, south, east, and west sections of the element. There you go. That's a nice 6 for you. All right, so that is how we would draw the Lewis dot structure for these electrons. All right, I want you to meet a friend of mine. It's Bond, James Bond. Those of you that are watching, you get the magic mask, okay? All right, this is the mask that we'll ask you about. It's a stormtrooper mask. Don't tell your friends, because if you did the work and you actually watch this video, it's going to pay off for you. Don't help them out. All right. All right, so I'm going to introduce you to our friend bonding. And this is the way that atoms are attracted to each other to form molecules. Okay, this determines nearly half of the chemical properties we see. This determines how your body functions. This determines pretty much how all of everything works. Okay, it's all done through bonding, because everything is trying to reach that octet. All right, enough of that. All right, so let's talk about the different types of chemical bonds. Ionic bonding, that's one we're going to be hitting on pretty hard today. And then we have covalent bonding, and we have metallic bonding. Those are the different types of bonding. So now let's get into ionic bonding. It's hard to breathe with the stormtrooper mask on. All right, ionic bonds are going to be electrostatic forces that bind metals and nonmetals together. Oh, metals and nonmetals. One of those trends paid off. All right, so what's going to happen is they're going to form between a positive ion, which remember is a cation, because cats are positive, and a negative ion, which is what we call an anion. Looks kind of like the word onion, and onions can sometimes cause tears, so you might think of that negatively. Or I just may be reaching. All right. Here's a nice little cartoon that relates to ionic bonding. Okay. So, again, ionic bonds are formed by these electrostatic attractions between positive and negative ions after the transfer of an electron from a metal to a nonmetal. Because remember, who's given up their electrons? It is the metals, okay? So these metals over here, right? They like to give it up. They're the losers, okay? And then on the other end, over here, we have the nonmetals. These are the gainers, okay? So we're transferring from a metal to a nonmetal. So that means if we're getting rid of an electron, what kind of charge would these take on? If you're going to get rid of a negative charge, you're going to do what? Become more positive, right? If you're taking on a negative charge, you're going to become more negative. And so this is the description of an ionic bond. The nonmetal attracts the electrons because it is much more electronegative. So remember, Father Fluorine, the most electronegative atom of the periodic table. Chlorine sits right next to fluorine. Sodium here bows down to chlorine and gives up his electrons. I think that's from a game. We couldn't figure out what game it's from. I guess I'm just too old. All right. So you'll remember the trend, electronegativity. That is the power to attract electrons. Over here, we've got really electronegative atoms. These guys really want electrons, because if they get just a couple of electrons, they will reach their noble gas status, okay, and they will fulfill their octet. So these guys have really low ionization energy, so it means it's really easy to take those electrons off. So because they have a low ionization energy, it's going to be really easy to just pull those electrons off of them because they want to get rid of them in order to reach their octet. These guys want to gain them. So having these two variations between the trends makes total sense. So these that are highly electronegative, they're really reactive because they have a very strong tendency to capture electrons. They just want to rip electrons off of everything. These are also highly reactive because they have a tendency to really want to get rid of their electrons. So they give up their electrons really easily so that they can achieve their octet. So what's the chemical formula? Or how do we establish the chemical formula of an ionic compound? Maybe Shaq knows. All right, so one way is we can use the Lewis dot structure to determine the formula. So the example we're going to give you is going to be sodium fluoride. So first thing we do is draw the Lewis dot structure of each atom. So here we have sodiums and here we have fluorines. Okay, so sodium has one, what happened there? I don't know, one valence electron. Okay, fluorine has, I'm going to do this in a different color. 3, 4, 5, 6, 7. Okay, fluorine has 7. Sodium has 1. Altogether, that's 8. Just FYI, it's 8. Okay, so there's the Lewis dot structure for each atom. Don't ask what that line is because it was organic. It just happened. Okay. All right, so then we're going to draw arrows and we're going to move electrons to fulfill the octet rule. Okay, sodium had 1, fluorine had 7. So are we going to get rid of 7 electrons off of fluorine in order for sodium to be happy? Heck no. We're going to get rid of 1 electron from sodium and it's going to go over to fluorine to be happy. So here's what it kind of looks like, okay? The difference being, in the Lewis dot structure, we only show those outermost valence electrons. It's showing all of sodium's electrons here. It's showing its inner electrons. Disregard those. Pay attention to just the valence electrons. So you have the 1 valence electron from sodium. Here it is right here. Boom. Okay, and it's going over here onto fluorine's outermost energy shell to give it that happy 2, 4, 6, 8. That's what it's going to do. Let's see if I can erase this. Ooh, nice. I can't erase it. Okay, so again, Lewis dot structure, we only show the outermost valence electrons. This GIF is great because it shows you the animation of what's happening with those valence electrons, the transfer of 1 electron from sodium to fluorine. Okay, so that fluorine now has 8 in its outermost energy level, but remember, only the outermost valence electrons. Make sure you only write the valence electrons or Shaq will dance. All right, so then we need to add brackets and charges to designate that it's an ionic bond. Okay, so in order to designate it's an ionic bond, you're going to add these brackets and charges. Now, fluorine gained 1 electron. If you gain an electron, you're gaining a negative charge. It is going to give that, it's going to give that atom an overall negative charge. So you need to make sure that you designate that negative charge right here. So right here, you can see after fluorine has taken on sodium's 1 electron, it is going to, there's sodium's 1 electron that it's going to take on, it's going to take an overall negative charge. Sodium, by giving up that 1 electron, is going to achieve a positive charge because now the protons are winning in sodium and they're winning by 1. So the 1 is implied here. You don't write the 1, it's implied. If the charge is even there, it means it is charged and the 1 is implied. Make sure you only write the valence electrons or Shaq will dance. Okay. All right, so again, here is our Lewis dot structure. Here's our sodium with our 1 valence electron. Here's our fluorine with our 7. Okay, and sometimes it's nice when you're writing these out, I would give sodium circles and I would give fluorine maybe X's. It's totally your call. It's really nice to use colors, different colors, so fluorine's purple, sodium's red. either way. Okay, so sodium's going to give up, because it's a metal, it's giving up its 1 valence electron to fluorine. Fluorine, the nonmetal, is taking it on. Okay, then the way that we draw this is sodium with its plus charge, because now the protons are winning by 1, and fluorine with its overall negative charge in those brackets to show that this is an ionic bond. Okay, and then our ending compound is sodium fluoride. So now, let's write the chemical formula for lithium nitride. Again, first draw the Lewis dot structure of each atom. Here we go. There's lithium, here's nitrogen. Okay, now let's take a look at our valence electrons. Lithium has 1. All right, so it's very reactive. It's going to want to get rid of that 1 electron. Lithium is our metal. Okay, here is our nitrogen. Nitrogen, it has 1, 2, 3, 4, 5 valence electrons. So nitrogen is going to need 3 electrons in order to reach its octet. Nitrogen is our nonmetal in this case. All right, so now we're going to draw arrows and we're going to move electrons to fulfill the octet rule. So lithium is going to give up its 1 electron to nitrogen. Then we're going to have another lithium. Another lithium is going to give up 1 more electron to nitrogen. So far, the nitrogen has taken on 1, 2, okay? Right now, nitrogen has 7 valence electrons. We need to add 1 more lithium and 1 more lithium electron, and now the nitrogen has its octet. Okay, you can see now that nitrogen has 2, 4, 6, 8 valence electrons. It's happy. Okay, it's just like a noble gas. So, now we're going to show the charges on the newly formed ions. So lithium lost 1 electron, so the overall charge for lithium would be +1, because those protons are winning by 1. The nitrogen gained 3 electrons. The overall charge for that nitrogen would be -3. Okay, so now we need to combine the newly formed ions to make the compound. Now we had to use 3 lithiums in order to completely fulfill that octet of the nitrogen. So now to write the compound, you would have to say Li, and then you put a subscript 3, which means we use 3 of them. There are 3 lithium atoms bonded to 1 nitrogen atom. Okay, so you're going to say 3 positive lithium ions plus 1 nitrogen ion, which has a overall charge of -3 because it's taken on 3 electrons, which will give us Li subscript 3N. The 3 again stands stands for how many lithium atoms are there within the compound. And in this case, it's 3. The way that we would write this in brackets, this is how we want you to write it to show that it's an ionic bond, is you would show Li in brackets with 1. See, now notice in the outermost shell, you don't have anything because it's given up its last electron. Okay, so here are your 3 lithium atoms. All of your lithium atoms are in brackets and they have a positive charge. Now here is your nitrogen atom. It's taken on those 3 electrons from lithium, and it has an overall -3 charge. Now instead of putting a minus, 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 we would have you put -3 or 3 minus would work. Just a numerical representation. Is there an easier way? Of course there's an easier way. Okay, so once these compounds are formed, they do not have a charge. It is neutral. The compounds, okay? So that means with neutral, your number of positive charges has to equal out your number of negative charges. So that's in order to get a neutral compound. All right, so lithium combines with nitrogen. Lithium is +1, nitrogen is -3. Okay? So nitrogen, because it's -3, it's going to need 3 positive charges in order to make this a neutral atom, which means it's going to need 3 lithiums to balance this out. We do something that we call the crisscross rule to make this a little bit more simplistic. So our example is aluminum chloride. Step 1, write the symbols and the charges of the elements. So our cation, our metal, and in this case, aluminum, is going to be written first. So there's our aluminum, there's our chloride or chlorine. Okay, aluminum has a +3 charge. How do we know that? Because we went to the periodic table and we looked at what column it was in. Okay, aluminum is in the 3rd column. 13th column. 13th column? It's 13th column. I'm amazing. Yeah, you can thank me later. So aluminum's in the 13th column, which is 13 minus 10, 3. Okay, so that means aluminum has a 3+ charge. Chlorine has a -1 charge. Okay, so you're going to crisscross the charges and then when you crisscross them, so that means you're going to take the charge for the aluminum and you're going to crisscross it so it goes down to the base of chlorine. You're going to take the charge of chlorine here and you're going to crisscross it so it goes down to the base of aluminum, and you're going to write them as subscripts, but not with the plus or minus, just with the numbers. Okay? So the way that looks is, yep, the 3 from the aluminum comes down to the base of the chlorine as a 3, no charge. Okay? The 1 from the chlorine comes down to the base of the aluminum. Now, even if you write aluminum, you're implying that 1 atom of that element is available. So it's sort of implied. You don't write the 1s usually. It's sort of implied that they're already there. So then you're going to combine it as one formula unit, and what that looks like is AlCl3. Okay, so aluminum has a +3 charge, chlorine has a -1. It's going to take 3 chlorines to balance out the charge of this aluminum so that we have a neutral atom. The resulting formula unit then would be AlCl3. I'm sorry with the coughing, I apologize. Oh, that ends our broadcast for today. I hope that it was helpful. If you have any questions, please make sure to talk to Miss Herman, talk to myself, talk to Miss Risto. We would be happy to go over them with you. For those of you watching, thanks again, and we'll see you next time.